Okay. So just for background, I'm an astrochemist, so there'll be a little bit of chemistry flowing into this, and that's because I'm going to try to sort of outline a generic context of how the Earth came to be with volatiles on its surface. And so then I figured I should start with the definition of what is a volatile, and I got this one from David Catling, who's an atmospheric scientist, and it's a low melting or boiling point present as a liquid or a gas in a planet's hydrosphere, which is basically where the water is. It may be in the ground, maybe in the oceans, or maybe in the air. And the atmosphere. So that's one definition. That's not the definition that I am going to work off of, because we're talking about the earlier stages, how things get implanted into solids. The Earth is made of solids. And so I'm going to define a volatile as basically a low sublimation temperature where it is present in the gas. So to outline the basic construct of why this is an interesting question, I'm going to look at the carbon content of basically the solar system. So I'll have the sun here that represents, the sun got everything, all right? And I'm going to, in this case, plot a total carbon content relative to silicon. Why silicon? Because the Earth is made of silicates, right? The Earth is a silicate magnesium rock. And if you look at where the Earth is, it's down here, at least the part of the Earth that is the mantle. So this is the Earth. Is highly depleted in carbon relative to the sun. All right? And now, it's a little tricky. That is, if we look in the Earth's core, the density of the core is below that of iron and nickel at high pressure and temperature of the core. So we know that there's actually a light element or elements in the Earth's core, and that could be anywhere from hydrogen to silicon. So what my colleague Jackie Lee at Michigan did is we just asked the simple question, well, let's suppose it's just carbon that's the polluting element in the core, and what is the constraint set by that? And you get what we would call a strict upper limit to the bulk Earth carbon content right here, which is still highly depleted by at least a factor of 100 or more. Since this is a very strict upper limit, it's probably much less than that. If we go outward in the solar system to, so this is 1 astronomical unit, and that's right, I need to define some things here. So we have definitions. 1 parsec is 206.265 astronomical units. An astronomical unit is an Earth-Sun distance. Parsec is something we use in the galaxies, and 1 astronomical unit is of order 10 to the 13th centimeters. I make no, my field uses CGS. You're going to live with it. All right, so there are some definitions. I'm going to have to erase that, sadly. Okay, so big scales. If I go out to the asteroid belt, so that's a few AU, you get to basically meteorites, and they are down here sort of close to where the bulk Earth is. And even the most primitive meteorites, the so-called CI chondrites, if you look at the abundance of elements in the CI chondrites, they basically track the sun. And in fact, if we can't determine the abundance of an element in the sun, they go to the rocks to figure what the sun's abundance is. But carbon is depleted in those rocks. And if we go beyond Jupiter, so it's sort of greater than 5 AU, we get up here to comets, and they appear to have all the carbon that the sun has, by and large. All right? And I could make the same plot, this is carbon, I can make the same plot for water. So that is the inner solar system, Mars, Earth, everything, are water poor. We obviously still have some water. And the outer solar system is water rich. So how did this come to be, right? And is this a common occurrence? And I'm just going to work out some basic concepts as to how this came to be. But the ultimate goal is if we can understand this, then we can pivot and look at all these other planets that are out there and try to understand whether their formation histories are similar to our own. Okay. So now, yes?
And what's the ratio, just out of curiosity, of carbon over hydrogen and helium in the sun?
Okay, so it's a very good point. So the Earth is oxygen rich, right, because of the silicates. The Earth is hydrogen poor because hydrogen only came from water, by and large. Okay? And so the carbon content of the Earth dwarfs the hydrogen content by some factor. I can't do it on the top of my head right now, but the Earth has more carbon than it does hydrogen. And it all comes down to basically how the water was supplied and how the carbon was supplied. And they probably were supplied together. And a typical comet it's about, by weight, 25% water, which is lighter, and about 20% carbon, which is in heavier forms, right? So, in different forms. So, of order, a comet would be 1-to-1, carbon to hydrogen of order. The Earth is much less than that. And the sun got everything, or so we posit. And the hydrogen, the carbon to hydrogen content, carbon relative to hydrogen in the sun is of order 10 to the minus 4 in a relative sense. Okay? And, I'm an astrochemist. Mostly I put things relative to hydrogen. But when your body doesn't have any hydrogen, you kind of have to think of other things. Okay? All right. So before I get to the physics of star and planet first, we have to understand or outline the basic constructs of star and planet birth and how we probe it. So stars are born in molecular clouds. And these things are, of order tens of parsecs. So, 206, 265 times that number, solar system. So vast scales in the galaxy. And I'm going to fill in the sort of generic properties of these bodies once I outline the probes. All right, so I have this giant molecular cloud. And inside the giant molecular cloud are sort of denser filaments. They're denser by a factor of maybe 10 or 100 above that of the cloud itself. And these are of order, parsec scale. All right. Then regions of the filaments, gravity starts to win, and you get condensations. And we call these essentially pre-stellar cores because the star is not born yet. And now we're getting closer to the AU scale. We're about 1/10 of a parsec, or 20,000 AU. All right, that thing collapses, it's rotating. Angular momentum is conserved, and it basically collapses to a star and a disk and maybe some outer envelope. All right, when the star is accreting material, it also ejects it. It jets along its poles, and there are also more wide-angle winds. So we have a star, a disk, and an envelope. Okay, so we have and eventually the envelope dissipates away from the wind, blows it away, and you just have the star and the disk sitting around, and that is the main phase where planets are born. And I'm going to explain that in a minute. Okay, so now we have our probes. There's two probes, of which one of them, molecules, is full of multiple probes, because different molecules have different, they're different tools, essentially. So our probes, the first one I'll talk about is molecules. So generally when you think of, interstellar space, it's filled with hydrogen. All right, hydrogen emits, there's the spin-flip transition, but the primary thing to think about for hydrogen, it has an electron that can go up into different states, right? So there are electronic states. Now molecules have the same thing, right? You have some sort of complicated nucleus with protons and neutrons, and then just a bunch more of electrons zipping all over the place, right? So we have electronic states. That's one. Now another thing the molecule can do that atom doesn't is the molecule has structure and it can vibrate. So if I take water, I can have this mode, I can have this mode, and then I can have the sort of rocking mode. So a whole bunch of different modes. So there's vibrational states. And then, of course, it can also rotate. So rotational states. So what was realized in, sort of the mid to early years of quantum mechanics is that if you treat the nuclei as fixed, so this is fixed in motion, and the electrons are zipping around, that you can separate the wave function instead of one complicated thing into three still complicated things associated with the electronic states, the vibrational states, and the rotational states. All right, and this is what was called the Born-Oppenheimer approximation, or Max Born would say it was the Oppenheimer-Born approximation. So if we go here and say the diameter of a typical molecule is of order an angstrom. All right. And from the uncertainty principle, so we have the change in momentum, sort of change in location is greater than h bar over 2. Okay? So I can I know the size here, all right? So I can then, say that my change in momentum is of order, h bar now over 2 times my diameter of the molecule. All right? And the energy of that change in momentum, right, is delta p squared, over 2m. All right? So I know the change in momentum. All right? And if I stick the mass of an electron in here, all right, with that size, you find that for the electronic states here, that it's typically, of order an electron volt. Or I like to think in terms of temperature, it's about 10,000 Kelvin. For the rotation, you put in the mass of the nucleus, you will find that this is in the milli-electron volt range of order 10K. So that's a pretty impressive probe there, right? Something that's spanning a range of energy states. Now for the vibration, it gets a little bit trickier. You can't play this same simple game, and obviously This is very, very simple. But for there, you just use Hooke's law. So if I have my OH in a water molecule, all right, the vibrational frequency is 1 over 2 pi square root some force constant over the mean molecular weight. And the force constant for water, you can calculate it. It's not easy to figure out. It's, in this case, it's Newton. It's about 800 Newton per meter. All right. If I stick that in the mean molecular weight for water and that vibration, it's of order 10 to the 14 hertz. All right. And then if I do my h nu over k, energy, right, in this case putting it in temperature terms, it's of order 5,000 Kelvin. So there you go. The rotational states probe the really cold stuff. Vibrational states probe the warm stuff. And the electronic states probe the hot stuff. Okay. And it's also the case that the structure of the molecule can matter. So if I take ammonia, where it has this structure, this is what's called a symmetric top. So it has symmetry along 2 axes. And this turns out to be an amazing temperature probe. A really annoying molecule is methanol, because this hydrogen can pop within the potential of these 3 H's here, and that's a so-called torsional motion. And so the spectrum of methanol is just a pain because of this. All right. So now the other probe we have is what we call dust. All right. So if I were to look towards the center of the galaxy, there'll be all these stars. And very early on, it was noted that there were some spots that were completely dark. You didn't see stars in them. And back, the 1900s, they were referred to as voids. All right. And then along came knowledge of the stars from Cecilia Payne-Gaposchkin and Annie Jump Cannon. And we knew something about how to tell what the spectral type of a star was and get its luminosity. And then Trumpler went out and realized that if looking at a star get its spectral type, it appeared to be less luminous. Right? These two things didn't add up. So that meant space wasn't empty and something was absorbing. And in fact, it was preferentially absorbing in the ultraviolet and the optical. And then in the 70s and 80s, well, 80s, we developed the ability to look in the infrared. And if you went out to say, in the optical wavelengths, this thing would be dark. If you go out to 2 microns, you start to see the stars behind it. All right? And so that told us something about the size of the absorbers. And, the sort of average size of the absorbers is basically of order the 10th of a micron. All right? And in fact, you could get the size distribution. And it goes as something like the size to the minus 3.5 power. So most of the mass is concentrated in the bigger things and the surface area in the smaller things. And the other thing that came out of this is you can sort of get an average kind of cross-section. So the number density of the dust, the surface area of the dust is equal to about something like 2 by 10 to the minus 21 times the density of the gas. And that's in this weird unit of centimeter minus 1. This will come in handy a little bit later. Okay, so then, what is this stuff? Right? What is it made of? So the way that was done is you had your Hubble Space Telescope out here with its nice little solar panels, okay, observing a star that's bright in the ultraviolet, and it's peering through some sort of diffuse cloud that has some extinction and lets the ultraviolet light and the optical light through. All right? And what they realized is that what was missing from the gas, based upon some standard, and at that time we used the sun as the standard for abundances, but now we can use other stars. You know that basically what was missing from the gas was all of the silicon, all of the magnesium, all of the iron, maybe 30 to 40% of the O, and so what is that? That's silicates, right? Just go down to the beach there, right? And the other thing that was missing was about 50% of the carbon. So interstellar grains out there are mostly silicates and some sort of actually probably hydrocarbon. Now why this matters is that these grains, a tenth of a micron grains, are the seeds of rocks like the Earth. In the disk, there's a big party that goes on, and they grow and grow and grow to bigger and bigger sizes. All right? Now from the perspective of this problem, it gets even worse, because now I have ISM dust here. That what's provided to a planet-forming disk is an awful lot of carbon in the solids, and it don't make it to the planet itself. All right, so from the gas, what we can get is the density of the gas, because the gas, these gas phase molecules, these states are excited by collisions. So the frequency of the collisions gives us the density. We can get the temperature of the gas. We can get the velocity field of the gas. And we can even get abundance. All right. From the dust, I can get, well, really what I get is the surface density of the dust, which is in grams per centimeter squared. I can get the temperature of the dust. And actually, we know from various means that the ratio of the gas mass to the dust mass is 100. So I can equate the dust quantities to what's going on with the gas. Okay? So now, we can go back here and start filling in what's going on in terms of actual numbers. And I'll just riff for the moment. So the density of this material is of order 500 particles per centimeter cubed. And that's hydrogen, molecular hydrogen. The temperature we can measure is over 20 to 40 Kelvin. And the lifetime of this phase, and this actually is done by looking at other galaxies, is 10 to 30 million years. And the clouds spend most of its time quiescent. And that was from looking at galaxies like M51, which is face on in the sky. The filaments are a little bit denser. You're getting to 10 to the 4th particles per centimeter cubed. And just for reference, the density of air in this room is of order 10 to the 19 particles per centimeter cubed. All right, the temperature is getting cooler. It's like 15 to 20 Kelvin. And my lifetime for here is of order 1 million years. All right. Now the prestellar core has a density, much more of a density structure. So this is radius. So here's the center, and here's my tenth of a parsec, and this is density of hydrogen. It has about 10 to the 5th to 10 to the 6th centimeter cubed, and it goes down to maybe 10 cubed. It's kind of flat for a bit, and then goes down. And the temperature, I'll stick over here, it's about 20 K, whatever the filament is. Here's 10 K, and it kind of goes like that. And it falls to actually maybe 5 degrees above absolute zero in the center of that body. All right, and one of the reasons why stars are born here is, in the absence of magnetic support, you just have pressure supporting against gravity, very low pressure, with the temperatures being this low. So the stars are born in molecular clouds. There's a reason for that. All right. And the disk, so lifetime, I guess I have to put lifetime here. So the lifetime of this phase is, usually 0.5 mega years, maybe a million years. Okay? The star and the disk, the densities can range. All right? So close to the star, very high. Further from the star, lower. The disk is flared somewhat, so the densities in the midplane are high, low, upwards. It's hotter closer to the star. Get the idea. So the lifetime with the envelope is of order 0.5 mega year. And without the envelope, so that's just the disk and the star, it's a few million years. All right, well, so there's the probes. That sets up trying to understand what's going on in terms of the volatiles. And so for that, we have to talk chemistry. All right, so what do I know? So for the chemistry, I know we have low N, low density, very low temperature. And if a star is not nearby, I have an energy problem. I mean, these things are 10 K-ish. Where'd that energy come from, right? So low density, what that means is we're not in what we call thermochemical equilibrium, the chemistry of that atmosphere out there, all right? If you know the temperature, you can determine the composition. Here we're in the kinetic regime. And what does that mean? That means time matters. All right, I'm at 10 K. Whatever those reactions are, they can't need energy. They have to be exothermic. They have to generate energy. But I still need a source. It has to come from somewhere. And it turns out it comes from cosmic rays. So cosmic rays are energetic particles coming from supernova. They pervade the galaxy. The low energy regime of that spectrum will ionize H2. It makes H2 plus an electron. That H2 plus will immediately find an H2, make this molecule H3 plus, and it stops there. That doesn't react with H2, and that spreads the energy around and makes the chemistry that is observed in these objects. And so we make CO, you can make N2, You can make water. All right. So I'm making molecules in the gas. But these molecules are colliding into each other, and as they're getting denser and denser in this prestellar core here, they might collide with a grain with greater frequency. So maybe we're also making ices. And that's kind of important if you want to think about making a terrestrial well, right? It's the solids. It's made from the solids.
What about the energy from gravitational collapse?
So that will come into play in a little bit. It's super important for determining the volatility, the survival of volatiles. So the way to think about this, and it's kind of neat, is, we have a spherically symmetric mass distribution when gravity starts to win, so you can figure out the free fall time scale. So that's your dynamical time, if you will, right? So it's 3 pi, we have 32g rho, okay? And I could take my density here in the center, 10 to the 5th, and work that out, and it's of order 10 to the 5th year. All right? So for a molecule, I have to work out its time scale here for what happens when it interacts with a solid. So I'm going to call it depletion. So there'll be a rate, and it's per second. And so that is the number density of grain, sigma grain, the velocity of the gas, and a sticking coefficient. The sticking coefficient is, when it hits the grain, does it bounce off? And that's a constant of order unity. That's an ode to all the cosmology classes. But actually, we measure this in the lab. The sticking coefficient is indeed about 1. N grain, sigma grain, we actually got from the analysis of dust. The N grain, sigma grain in the interstellar median is of order 2 × 10 to the minus 21 times the density. The velocity of the gas is collision dominated. It's a Maxwellian distribution, so it's like 8 kT over pi mh is the velocity of the gas. So I can stick these things in. It's basically 2 × 10 to the minus 21 times the density of the gas. This is of order 10 to the 4th centimeter cubed per second. All right, and if you work it out, you find that it's 2 × 10 to the 9th years over my gas density, which is 10 to the 5th. So this is basically 10 to the 4th years. So that means before this thing can collapse, everything is finding a grain and freezing out. I'm making ices. All right? So then the next question is, do the ices survive? Right? Do they spend any time on that grain? So we have, say a water molecule sitting there and it's zipping around, and here's a grain. So you'll have some sort of potential surface here. Here's my 0. And what the potential well looks something like this. It comes out to 0 here. So there's a deeper well closer. So this is surface of the grain. So this is what's called chemisorption. And the binding energy, the energy associated with that bond, is of order an electron volt. So EB is the binding energy. All right. To get to this stage, we have to break a bond. We have to overcome a barrier. And you're at 10 K. There's no energy to break that bond. So instead, what matters is this one here, which is what's called physisorption. What physisorption is as that molecule approaches the grain, it has an induced dipole-dipole interaction, and it's basically a van der Waals force. So the strength of it is proportional to the polarizability of this and the polarizability of that. All right? And this has a binding energy of order 1/10 to 2/10 of an eV. All right. So now, how do we get a molecule off? What happens is the molecule is vibrating up and down in that well, and has a typical vibrational energy. So this is sublimation, my rate of sublimation per second. So it has this vibrational energy, which is of order 10 to the 12th hertz. And there's a way to figure that out. It's vibrating, and it has a chance at each one of the vibration that it's going to come off. And it's an exponential of EB over T or KT, depending upon what units your binding energy is in. All right, so for water, the binding energy is of order 5,000 Kelvin. So if I have, K sublimation H2O here, that's 10 to the 12th times e to the minus 500, since T is 10K, and that's greater than the age of the universe. So that water molecule ain't coming off. And the binding energy of Cl, which is less polar than water, is of order 1,000 Kelvin, and at 10K, even CO is not going to come off. So we're making ices. All right, and what I can do is I can say, what is the sublimation temperature, which is, where the temperature where K depletion equals K sub. And I would have my silicates, refractory carbon, and water, CO2, CO, N2. And the sublimation temperature for silicates is of order 1400 Kelvin. Refractory carbon is probably more of a distribution, but around 500 Kelvin. Water might be 120 Kelvin, it's pressure dependent. CO2, 70 Kelvin. And CO and N2 are of order 20 Kelvin, the most volatile, all right? And what's provided to the disk in collapse, essentially for carbon, the carbon is about, it's CO plus CO2, that's 50% of the carbon, and then plus the refractory carbon, which is the other 50%. The hydrogen's coming in water, 100%. And some from the carbon, actually, but mostly water. And the oxygen is, of course, mostly coming in the silicates. Plus, maybe 30% water, and the remainder is CO and CO2, since they're also carriers of. So that's what provided to the disk. Now we have to think about planet formation. What am I doing here? 5 more minutes and I'll be wrapped up. So, for planet formation, we started about 1/10 of a micron. All right? Grows via means, experts in the audience, gets to maybe planetesimal sizes, that's 100 kilometers, and then, of course, all the way onto Earth. The easiest way to affect these things and remove ices and break things apart is when they're small. Because when they're small, they can be heated to higher temperatures than when they're big, because there's more volume to store all that heat. All right? So it's easiest to lose volatiles via sublimation when things are young. All right? So what we have is we have a disk around a star, and most of the grains grow to about 1 millimeter size, and they're concentrated in the midplane. And we want to know what the temperature of that material is. So this is the temperature of the dust. Right? Here we are. This will be 1/10 of an AU. This is about 1 AU. Maybe this is 10 AU. And it depends whether the star is accreting. So that's the gravitational energy release or not. All right? So if the star is not accreting, we're in what's called the stellar radiation dominant regime. So here's my silicate temperature. So that's 1400 K. And then we have our refractory carbon, 500 K, and then say water, 120, and CO 20. What the it would look something like, actually I think it comes out like that. Okay, so what this means is that the refractory carbon, which is what I want to pay attention to for the Earth, is inside of 1 AU, the sublimation point. If I were to grow things to planetesimal sizes with these seeds, they would have cometary level carbon. That can't be. All right, so instead, this is at times greater than a mega year. If you go when the energy of accretion is being released, so this is the star, and this is star plus accretion. You have this point goes all the way out to beyond the asteroid belt, and I lose my carbon, I lose my water. I have to form planetesimals in this stage at times less than a mega year. All right, and actually we know that that happened in the solar system. Iron meteorites can be age dated via very interesting means, and big things existed within a few 100,000 years of the birth of the solar system. And this is why, at a baseline level, why they are volatile poor at birth. QED. Thank you. We have actual pictures of these things.
Question about this physiabsorption argument here. Isn't 5,000 Kelvin quite a high energy scale for physiabsorption?
So what happens is the water has the hydrogen molecules have sort of like an extra, the hydrogen bond, which is not really a chemical break bond, and it adds extra oomph to the physisorption. So it's on the high end of the physisorption range. Yeah, you were right. Okay, so we do have. So that's the schematic. That's what you saw, and that's reality. Right. So we have our cloud. There's a peach cell core. This is a particular molecule that traces the density. So you see it's centrally concentrated. There's the millimeter grains concentrated to the midplane. That's the white. The CO is flared. That's the CO in blue and red. And then you see a scattered light surface from an HST image. There's the jet. This is the millimeter solids coalesced in the disk. We think planets are born here, carving out that gap. And there's Saturn, because it was made via some method in this process.
Okay, the trivial question, but still, you mentioned this is 10,000 Kelvin for electron volt, right? I mean, for electronic sensor, and your vibrational energy is 5,000.
It's really closer to 2,000.
Oh, right. So it looks like too close, right? It's
Yeah. So
it's not special for water, or why it's kind of.
Yeah, so it's, no, you're right. It's typically, I was doing order of magnitude. So the typical vibrational transitions would have energies of order a few thousand Kelvin. But the water state that I worked out actually has that energy that I worked out. In any event, it's the electronic ones, which are really 10 eV or so. And so we see the electronic transitions of things that can survive, because any place where it gets really hot, there's ultraviolet photons present that break the molecules apart. And so the things that can survive are H2, CO, and water, because they have, via different processes, an ability to survive against that ultraviolet radiation. H2 is the one that survives the best. And we see electronic transitions for them, for H2, quite readily, 0.1 AU from the stars, where they're originating. Vibrational transitions are coming from about 1 AU, and the rest of the disk is traced by the rotational transitions.
Thank you.
Sure.
Yes.
Your bottom line was that in order to get the depletions of the terrestrial planets, everything has to form early when it's hot.
Yeah.
You get the heating. So, but of course things kept going through the later stage, the cooler stage. So we've talked about it as a binary. Can you say a little more about that sort of that transition? How much has to happen early and how much can still happen later?
Right. And therein lies the rub. That's correct, because this is a binary argument here. This would lead to an Earth with no carbon and no water. So then the question is, well, where did the Earth get its water? And there's two possibilities for that. One is that the solids in the disk are subject to a force, an extra force. So the gas is rotating at Keplerian velocity, but it also has an additional pressure support term, and that pressure support term is negative. So the gas is orbiting almost as if it was around a star that was lower mass, and that was a great suggestion from Ruth. The dust is orbiting at the Keplerian, so it feels a drag force, and it goes inward. So maybe it's drift, but there's an awful lot of carbon in that outer disk, so if drift is providing, you have to stop the drift, because otherwise you just get too much. That's one possibility. The other possibility is when planets are born, dynamical simulations, experts are in the audience, show that you can throw things around, and maybe you get things later. So.
That method makes all this process.
I'm sorry?
That method makes a
Not in this process, okay, but in the molecular cloud formation and evolution, the dark matter plays a role in the potential of the galaxy. In general, I think most of the evolution of the galaxy is still under the weight of the baryonic matter, but I'm not an expert to say with 100% the dark matter doesn't matter.
Okay, thanks very much.